Okay, today we're going to move into section 3.2, which is where really the mole and its idea is introduced. Okay? At some point during today's class, you're going to get a handout that will, at some level, almost replace a whole bunch of stuff that's in that section. Okay? It's not different material, it's just more practice than what you see, and practice in terms of specific skills that maybe Gary doesn't focus on as much. Okay? So if we all understand the idea of relative mass, the masses of the elements are relative to each other when we're speaking of atomic mass units. Meaning, if carbon has an atomic mass of 12 atomic mass units, then oxygen with a mass of 16, that's 16 relative to the 12. Like 1 1/3 times as massive. Hydrogen would be 1/12 as massive. That type of thing. If I multiply those relative masses in atomic mass units, all of them by the same big number, the relative masses will still remain the same. In other words, if I have 100 carbon atoms and 100 hydrogen atoms, the mass of the 100 carbon atoms will still be 12 times the mass of the 100 hydrogen atoms. Does that logic make sense? A question we might want is, okay, if that's true, what if I can find the number that, big though it may be, that if I multiply the atomic mass units by, then I can put grams after those atoms. In other words, how many carbon-12 atoms would it take for that to mean 12 grams? Now that's going to be a huge number. But if I find that big number, then I multiply all of the atomic masses, the relative masses, by that same big number. And that means I will be able to put grams after each of those mass values, because I multiplied all of them by the same number. So let's imagine we know what that number is. And I multiply carbon-12 by that big number, big enough to put grams after. If I take that same big number and I multiply it by the atomic mass of hydrogen, I can now put 1 gram after that. The relative masses will be the same, except if the number's big enough, I can put grams after it. Okay? The question you might ask is, how big is that number? Well, it's this big. It's a big number. Now that number should convince you of 2 things. If it takes that many of any atom in the periodic table to allow me to put grams after the mass, then that must mean that atoms are unimaginably small. If it takes that many of them to put grams after them, okay? Now, how big is that number? Let's try to imagine it. This is one of the challenges of chemistry, because the things we're dealing with are so small. Even irrespective from the fact that we can't see them, the fact that they're so small, to have a measurable amount of them, we need an unimaginably big number because they are unimaginably small. And we're not talking about the things that make up the atom. We're not talking about the electrons and protons and neutrons. We're talking about the atom itself. And when you get into, well, what about the things that make up the atoms? What about the subatomic particles? Then we're getting even into a weirder realm, where matter doesn't even behave the way we think it should. But let's try to imagine how big that number is. That number, by the way, is given two names. One of them is named after an Italian chemist named Amedeo Avogadro. So it's called Avogadro's number. But it's also called a mole. Okay? So a mole of anything is that many. And if you want to put items, things, whatever, it's a big number. Moles are to atoms as dozen is to eggs. All it is a number. It's just a number. And it's that big because if we want to use grams, we need that many. But it's a convenient counting number for things that are damn tiny. We don't use moles for eggs because you can pick up an egg and look at it. Anything that's big enough to see, that number of them would be a ridiculous amount. But if things are small enough, then that's a convenient counting number. We don't use dozen for atoms because they're too small. And we don't use moles for eggs because they're too big. But that's all it is. It's a number. And remember the three ways we express amounts. Measure the mass, measure the volume, quantity, and we count them. Okay? So let's try to imagine how big that number is. What I'm reading right now is the first page of the handout I will give you eventually. Okay? There is a definition for the mole, and it's in what I'm going to give you. Okay? You don't necessarily have to write it down. The mole is a convenient number of atoms, ions, or molecules to work with in the laboratory because they are so small. This convenient number, Avogadro's number, and the flip side of this first page is all about Avogadro. Okay, and it's an interesting read. Also has significance in terms of the atomic mass of elements. A mole is defined as the number of atoms, so it's a number, in exactly 12 grams of carbon-12. Now, if you think back, that sort of harkens to our definition of one atomic mass unit. One atomic mass unit is exactly 1/12 the mass of a carbon-12 atom. But a mole of carbon-12 atoms has 12 grams. So the number of carbon-12 atoms in exactly 12 grams of carbon-12. Okay? If you try to imagine how big that number is, and there's a number of analogies out there, lots of them. Apparently this one was written by someone who lived in Alberta. Okay? It's called the green pea analogy. If you selected 100 average sized peas, 10 to the 2, you would find that they occupy roughly a volume of 20 cubic centimeters. 1 million peas are just enough to fill an ordinary household fridge. 1 billion, 10 to the 9, will fill a 3-bedroom house from cellar to attic. 1 trillion, 10 to the 12, will fill 1,000 houses, the number you might find in a medium-sized town. 1 quadrillion, 10 to the 15 peas, will fill all the buildings in one of, now it says, our larger cities, such as Calgary or Edmonton. Whether you consider those cities to be large or not is debatable. Obviously, you're going to run out of buildings very soon. Let us try a larger measure, for instance, the province of Alberta. Suppose that there is a blizzard over Alberta, but instead of snowing snow, it snows peas. Alberta is covered with a blanket of peas about 1 meter deep, all the way from Saskatchewan out to BC and all the way from the United States to the Northwest Territories. This blanket of peas drifts over the roads, banks up against the sides of the houses, and covers all the fields and forests. Think of flying across the province with this blanket of peas extending out as far as you can see. This gives you an idea of our next number. There will be in this blanket about a quintillion peas, 10 to the 18th. Imagine that this blizzard of peas falls over the entire land of the globe. North America, Africa, South America, Europe, Australia, and Asia. All of the continents are covered with peas 1 meter deep. This global blanket will contain sextillion peas, 10 to the 21. Then imagine that the oceans are frozen over, and the blanket of peas covers the entire land and sea area. Remember, the ocean takes up about 70% of the Earth's surface. Now go out among the neighboring stars and collect 250 planets the size of Earth and cover them completely with this blanket of peas 1 meter deep. Now you have a mole of peas. So that analogy should convince you again of two things. Atoms must be damn tiny, and a mole must be a damn big number. And it represents the center of any conversion between any of the other amounts of things. Volume, mass, and notice there's, in that first diagram, there's two entries for volume. Volume of a pure substance and volume of a solution. And that's what this section is going to be primarily about. Okay? Now, if we go to the work text, before we actually start doing anything, Gary has a few things to offer. Avogadro didn't come up with the number, it's just named in his honor. And the flip side of this handout kind of explains what that honor was about, okay? So let's guess about there. Not quite. No, I think that first paragraph is okay. I don't really like this definition. You have to reference carbon 12, so it's defined better up here, okay? So a mole is defined, and again, you don't have to write this down. You can read it when you get this. The mole is defined as a number of atoms in exactly 12 grams of a particular isotope of carbon. Carbon 12. That's the definition of a mole. And an isotope of carbon 12 has 6 protons, 6 neutrons. Okay? That many of them is the definition of a mole. Okay? The definition of the mole is under continuous review. It is fine-tuned periodically in response to new information about atomic structure, changes in the definition of atomic mass unit, and in fact, how precise instruments are, okay? The number of things in a mole is also referred to as Avogadro's number, in honor of the Italian scientist whose insight regarding gases led to a technique for determining the relative atomic masses of nonmetals. And remember, we kind of introduced that at the tail end of the last section. It's kind of easy to figure out the relative mass of things that exist as solids, because if we assume the formula is 1-to-1, we measure the mass before, we measure the mass after, we do the subtraction. But how do we do that for gases? How would we be able to confirm, or at least feel confident that this and this would have the same number of gases? okay? And that's kind of what Avogadro, who based his hypothesis on the work of a French scientist, made sense out of that. And you can read the back page of this if you want to. It has to do with in the 1700s, there was a lot of interest in France about hot air balloons, and there were a number of scientists investigating gases associated with hot air balloons. And gases fascinated a number of scientists. There was a French scientist named Joseph Louis Gay-Lussac, and he noticed that when gases combine in chemical reactions, they always combine in whole number volume ratios. And Avogadro looked at that and used that to develop his hypothesis more. We'll talk about Avogadro's hypothesis later, okay? Chemists currently estimate that a mole is 6.02214,179 times 10 to the 23, give or take a few million billion. Now, we're only going to worry about the first three significant digits. It doesn't really matter how many we go to. As based on our best efforts, the number of zeros is still massive, okay? So if this is where the guessing starts, there's still way more zeros after that we don't know for sure yet. And that's, again, that's just a testament to how small atoms are, okay? Just as a dozen is 12 of anything, a mole is approximately that of anything. While a dozen is a fairly small number, a mole is an absurdly large number. That's why we don't use an absurdly large number to represent amounts of things we can see, because that would give us an absurd amount of the material. We need the mole only because atoms are tiny. And it's, again, as a dozen is to eggs, a mole is to atoms. And if that makes sense, that's effectively the main part of this introduction, okay? The mole was introduced in the early 1900s by Wilhelm Ostwald. Ironically, Ostwald developed the mole concept as an alternative to the atomic theory, which he didn't accept. Even at the beginning of the 20th century, there were still people that were sort of pushing back in the atomic theory. Today, the mole is used throughout modern chemistry as a central unit through which all other quantities of materials are related. But it wasn't common before the mid-1950s, so just 2 generations ago. So if you look at the SI units, the SI unit for amount is mole, okay? And that's a number, it's a counting unit. Now, before we go into any calculations, if that's true, we can set up several ratios, okay? If a mole equals 6.02 times 10 to the 23, if we're talking atoms, that means a mole of atoms equals that many atoms. So the obvious conversion factor would be 6.02 times 10 to the 23 atoms per mole. Okay? Now, 6.02 times 10 to the 23 of anything equals a mole. It's just that we don't use it for big things. Okay? And what's the definition of a mole? The number of atoms in exactly 12 grams of carbon-12. So what we are also able to do, based on the introduction that I began the class with, if that many atoms has the atomic mass of every element in grams, then that means for every one of those elements, we can write something like this. 6.02 times 10 to the 23 carbon atoms equals a mole. what it also equals. 12 grams of carbon per mole. If we have this many carbon atoms, we have a mole. And that many carbon atoms has that mass. So 12 grams of carbon per mole is that many carbon atoms. Okay? So here's one conversion factor. Don't worry about the equal sign there. There's one conversion factor. This equals that. That equals that. Why does that equal that? Because 6.02 times 10 to the 23 carbon atoms equals 12 grams of carbon. Okay. That many atoms is in 12 grams. That many atoms is in 1 mole. Therefore, that number of grams is in 1 mole. Does that make sense? Now, what do we call that? We call that molar mass. Pick any element in the table. Put grams after its mass value per mole. So what's the molar mass of nitrogen? We'll stick to 1 decimal place for this discussion. 14.0 grams of nitrogen per mole. 121.7 grams of antimony per mole. 207.2 grams of lead per mole. Okay. A mole of any atom in the periodic table equals that element's mass in grams. That's why we use the mole. We can measure grams. And if every time we're measuring grams, we're also measuring moles, that makes this discussion pretty convenient. Okay? So this handout is all about molar mass and the calculations associated with it. I think maybe now would be an appropriate time to hand it out. What I'm going to do for you, because I'm such a giving person, every page on this worksheet requires a different type of calculation. It's all associated with moles, atoms, and mass. And there are a number of examples on each page. I'm going to go through each page and show you how to do each of them by doing one for you. Okay? In some cases, the space that's available is not really sufficient. And indeed, in some cases, how the example shows you how to do it is not sufficient. That's what I'm going to show you how to do it. Okay? Notice I've punched holes in it. You might want to save this. I don't know who wrote that analogy, whoever did. Obviously, in too much time on their hands. But it's only one of many. Gary has another way. I've seen one with eggs. I've seen one with soccer balls. Yeah. I don't think you need more than one to convince you that atoms must be really small. And that's why a mole looks so big. Okay? When you get these, as you turn the pages, you'll see that in the example part, some of them have an X through them, which means don't do it that way. That's why I'm going to show you how to do it. Okay? Now, if you don't think there's room when I go through these to fit what I'm doing on the board into the space available, then do it on a separate sheet of paper. Okay? The fact that so much of this is repetitive, thank you, is because it's supposed to be. If you can do these calculations on a test, then the vast majority of this stuff will not prove to be difficult. So you might wonder why there's so many of them on each page. The more practice you do, the more when you see it on a test, you'll know how to do it. Because when you're writing a test, you're never at your best. You're tired, you're stressed. Okay? And having that memory of how to do it is going to be something that's second nature. So I'm going to turn this off temporarily. And what I'm going to do now is at least begin this handout. It's not due for next class. I may even break with tradition and give you time in class to work on it, okay? So, this is a good read. I'm not going to read it now, but you guys can read it. This actually fits in a little bit with what Gary talked about when he was referring to Candace Arrow's paper. But let's start on this page, okay? Determine the number of moles of each kind of atom in 1 mole of the following substances. How would you do that? That's easier than it looks. You guys just did a test, some of which involved formula writing and naming. That's going to play into a question like this on a test. Let's start with another analogy. Let's say I had a tricycle. If I take 1 tricycle, how many wheels do I have? Awesome. If I take 100 tricycles, how many wheels do I have? 300. Got any calculator? What if I take 1,000,000 tricycles, how many wheels do I have? 3 million. What about 1,000,000,000 tricycles, how many wheels? What about a mole of tricycles, how many wheels? Pause. A mole is a big number. If I got a mole of tricycles, don't I have 3 moles of wheels? That's like saying a dozen tricycles is 3 dozen wheels. The mole's just a big number. Let's see if we can put that into a formula. Let's say I had carbon dioxide. In 1 molecule of carbon dioxide, how many atoms of carbon do I have? How many atoms of oxygen? Pretend this is a bicycle. If I have 100 carbon dioxide molecules, just like if I have 100 bicycles, how many wheels do I have? 200, right? If I got 100 of these, don't I have 200 of these? 100 of those? Let's say that's the seat on the bicycle, that's the wheels. If I have 1,000,000 bicycles, I got 1,000,000 seats, I got 2,000,000 wheels, right? I have 1,000,000 of these molecules, I got 1,000,000 carbon atoms, 2,000,000 oxygen. If I got a mole of bicycles, I got 1 mole of seats, 2 moles of wheels, right? If I got a mole of carbon dioxide, I got 1 mole of carbon, I got 2 moles of oxygen, do I not? That's all this first page is about. So each space in here begins with this. This is what I want you to write, in 1 mole. Okay? This is just counting. So let's try something for which the formula is not given. In 1 mole, number 3, sodium silicate. Silicate isn't on your table of ions. But what element is in silicate? What does the name suggest? Silicon, maybe? What element is silicon underneath in the periodic table? Carbon. Is there an 8 ion with carbon in it? In your table of ions, what's it called? Carbonate. What's its charge? 2 minus. Silicon's in carbon's group. So if carbon in an 8 ion is CO3 with 2 minus, do you think it's outside the realm of possibility that silicate might be that? That's what silicate is. Okay? So 1 mole of sodium silicate, that's the formula. Okay? In 1 mole of sodium silicate. Well, think back to the carbon dioxide of the bicycle or the tricycle. I got sodium, silicon, and oxygen. In 1 mole of that, how many moles of sodium do I have?
Two.
Say it.
2.
Otherwise, I'll think you guys are slow. 2. In 1 mole of sodium silicate, do I not have 2 moles of sodium? That's just like saying in 1 million of these, I got 2 million of these, right? Just make the number bigger. If I got a mole, I got 2 moles of sodium. How many moles of silicon?
1.
1. How many moles of oxygen?
3.
3. That's not hard, is it? Maybe if you're in preschool. But you don't learn chemical formulas in preschool. So, does that make sense? That's this whole first page. But you see how important it might be to know how to write the formula. Because if the formula is wrong, so's this. Okay? Let's pick another one. How about let's pick a hydrate. Iron 3 oxide trihydrate. So what do you write for that one? In 1 mole, iron 3 oxide is this. And when it's hydrated, it's rust. And actually, rust can have different numbers of water molecules. That's why some of the color differs. Now, the reason I don't want you to do it this way, number 1, because they don't even put moles in this example. But number 2, if there's water in the hydrate, they leave it together. Don't do that. Separate all the elements out, even if in the molecule, even if in the compound it's water, okay? So, how many elements do we have here? We have iron, we have oxygen, we have hydrogen, correct? So, how many moles of iron do I have in 1 mole of iron 3 oxide trihydrate?
2.
2. 2 moles of
3 oxygen. 6.
how many moles of oxygen? Not 3. I got 3 here, but I got 3 more there, right? So 6. 6 moles of oxygen. How many moles of hydrogen?
6.
6. Make sense? That's how you do all of these. Now, why do we do that? Well, we just defined molar mass, didn't we? If I know how many moles of every element there are in the compound, can't I also calculate the number of grams of every element in that compound? And if I add it all together, I'm going to get the mass of a mole of the compound. Okay? Okay. Every time we go to a new type of calculation, we have to do what we did on the previous page plus something else. Okay? And this is why you kind of got to pay attention to the way I do it. I put, looks like a rather energetic X through that one. What do you think's wrong with this, by the way? What do you think I don't like about that example, which is to say, don't do it that way? Anything missing? Sorry? Units. Precisely. Where do the grams per mole come from at the very bottom? There's no grams, there's no moles in any of the calculation until the very end. That's why I put an X through it. That's why you shouldn't do it that way. So what I'm going to show you on the board is exactly how I want you to do all of these. Now, there may not be sufficient room in the space available. Fine, do it on a separate piece of paper. Okay? So, let's pick one that looks intimidating. Sodium carbonate decahydrate, perhaps? Notice no formula is given. So we're going to do what we did on the previous page, except we're going to leave a little space between each of the number of moles of each atom, and you'll see why. So, in 1 mole sodium carbonate decahydrate. Now we're just going to count the atoms of each element. 2 moles of sodium. Everybody agree with that? Any argument there? How many moles of carbon? Just 1. Well, let's put a little space between them. You're going to see why soon. How many moles of oxygen? Don't say 3. 13. 10 from the water, 3 from the carbonate, right? So that's 13 moles of oxygen. And that means 2 moles of sodium atoms, 1 mole of carbon atoms, 13 moles of oxygen. How many moles of hydrogen atoms? 10 times 2. Okay. Now that's page 1. But what we want to do is convert these to mass amounts. And anytime you're converting mass to moles or moles to mass, you go to the periodic table, because that's where the mass values are. Okay? And obviously you're not carrying one of those around, but you do have the mass values on your periodic table. Okay? And in terms of precision, all of these are to 2 decimal places. Let's go to 2 decimal places. Okay? So, we want to convert moles of sodium, not to draw the arrows, I'm just showing you what we're doing, into grams sodium. So what unit has to cancel? Think back to what we did on our first test. Moles. Moles has to cancel, right? You don't have to write moles of sodium, it's obvious. Let's replace the arrow with the multiplication sign. Where do we get that from? Periodic table. According to the periodic table, 22.99 grams of sodium exists per mole. That's from the periodic table. I want to turn carbon into grams. According to periodic table, 12.01 grams of carbon exists in every mole. That mass of sodium equals a mole of sodium. So that conversion factor equals 1. That mass of carbon equals a mole of carbon. So that conversion factor equals 1. According to the periodic table in your book, 16.00 grams of oxygen in every mole. And according to your periodic table, 1.01 grams of hydrogen per mole. Okay? Now, I'm not going to the same number of decimal places as the periodic table on the wall. I'm using what you're going to get on your test. So, now just do the arithmetic. Show the units canceling. We're converting a number into a mass. 22.99 times 2 is what? 45.98, I think. 45.98 grams of sodium. So in other words, in a mole of that compound, that much of it is sodium. Okay? That much of it is carbon. In a mole of sodium carbonate decahydrate, 16 times 10 is 160, 16 times 3 is 48, so 208 grams, I think. 208 grams of oxygen, and 20 times, what is that, 20.2 grams hydrogen. Agreed? So in a mole of that compound, this is the mass of all the elements. Now do this. What do you get? What's the mass we end up with? And give it to me to 2 decimal places. You can see why there might not be sufficient room on the worksheet, right? What do you get?
4,800.
4,000? No.
186.
Oh, I forgot.
How much?
286.19.
286 point,
19.
which,
19.
give me the numbers. 286.19.
19.
286.19. What? What do you mean? Grams, but more than just that. Grams per mole of the compound. That means anytime I have that much of this, I know I have a mole. What this page is really allowing you to do is that once you've got the molar mass, you can go from any mass
That's the wheel.
to the number of moles. Or if you're given moles, you can go to mass. Does that make sense? Because now you have the conversion correct, right? Which means you could answer, if I got this many moles of sodium carbonate decahydrate, how many grams do I have? Or if I got this many grams, how many moles do I have? So is that a page that's coming? Yeah, that's a page that's coming. Now, for some of these, the formulas may not be completely obvious. Sodium hypochlorite, calcium carbonate. Actually, you should be able to do all these. What's the chemical name for number 4? The common name is asbestos, but what's the common name? Based on what you just learned in the last page. What's SiO3 called? Silicate, magnesium silicate. Yeah. So, and again, notice what they say here. List water of hydration as 10 waters. Don't do that. Don't do that. You can't look up the molar mass of water in the periodic table, but you can look up the molar mass of oxygen and nitrogen. So separate the elements up. As I said, I suspect you might not be able to fit that in here. Now, is it physically possible to write so tiny that you might be able to? But if you write that tiny, could you study from it if you can't read it? And once you do all of them, this page, if you do it that way, may fill up to the point that it's very difficult to study from. So it may be a better idea to do it on a separate sheet of paper. I don't care how many pieces of paper it takes you, as long as it's done, okay? Any questions on this? So notice what you do. You start with this, just like you did in the first page. That's all the first page did. Then you convert them to mass values from the periodic table. Cancel the units. Show me the mass of each element. And when you calculate this, don't just write that. Write that. Grams per mole. Okay. Am I going too fast? Are you guys with me so far? If something I'm saying doesn't make sense, if there's a logic that's escaping you, ask. Look at the next page. Why are we doing this? Well, given any mass, we should be able to get moles. Given any number of moles, we should be able to get mass. So this deals with the latter. You are given a certain number of moles of various compounds and asked, what's the mass of that compound? Well, you can't do that until you've done this. Once you get that, then Any number of moles you're given can be converted to grams. And I said, remember I said every time you turn the page, you gotta do what you did in the previous page plus something else? Once you get the molar mass, then you gotta do something with it. So there also may not be sufficient room here, because we're doing more than we did on the previous page. And again, there's no units until the very end, so skip that. Don't do it that way, okay? Somebody in here will, I guarantee it. Somebody, when they show me their worksheet, will do it that way, but don't, okay? I can't say it any clearer than that. It's just a reality that I've come to accept.
That circle is crazy.
Now I'm gonna pick one from this page. As a template for doing all the others. Let's see. What about cream of tartar? The first one. The chemical name is potassium hydrogen tartrate. Okay? So, let's do the same thing we did on page 1, then page 2, and then we'll do what this page asks us to do. All right? So we first got to find out the molar mass. We can't find the molar mass till we find out how many moles of each atom there are in the mole. Once we have that, we can convert it to grams. Once we do that, we get the molar mass. Then we can find the mass of 0.1 moles, once we know the mass of 1 mole. So, in 1 mole of potassium hydrogen tartrate, KH C4 H4O6. You might wonder why they don't put the hydrogens together here. Well, that answer has to do with the fact that the hydrogen tartrate anion, which is that with a -1 charge, is actually a weak acid. And that hydrogen is why. But that's again 12 time. Okay? Don't worry about why the formula looks that way. Just use it. So in 1 mole of that, how many moles of potassium do I have? 1. See how easy this is? It's embarrassing, it's so easy. 1 mole of potassium. How many moles of hydrogen? Not 4, 5, right? 1 there and 4 there. 5 moles of hydrogen. How many moles of carbon? 4. How many moles of oxygen? 6. So we did that on page 1, now we're gonna do what we did on page 2. We're gonna convert each mole amount to a mass amount. So according to your periodic table, what's the molar mass of potassium? 39.10. 39.10 what? Grams per mole. Okay? That's from the periodic table. Periodic table, 1.01 grams of hydrogen per mole. We want moles to cancel, which is why it goes on the bottom. Periodic table tells us 12.01 grams of carbon per mole. Now why isn't the molar mass of carbon exactly 12 grams? Average of what? The naturally occurring, starts with an I. Isotopes. If you harken back to Science 10 last year, remember we talked about radioactive elements? Some isotopes are radioactive, they got the wrong number of neutrons. So carbon doesn't exist as carbon-12. If all of the carbon out there was carbon-12, it would be 12.00000 grams per mole. But there's some of the carbon out there is carbon-13, which means it has 7 neutrons. And even a smaller amount is carbon-14, which has 8 neutrons, and that's radioactive. And that's what we use in carbon-14 dating. So this 0.01, there's no atom with that mass, that molar mass. That's just the average, okay? And oxygen, 16 grams of oxygen. So I'll show the units canceling. So in 1 mole of that compound, 39.10 grams of it is potassium. 5.05 grams of it is hydrogen. 48.04 grams of it is carbon. Let's see. 96? 96 grams of it is carbon. Okay? So what do we get for our atomic mass, for our molar mass, potassium hydrogen tartrate? The units we're going to end up with are grams of potassium hydrogen tartrate per mole. What do we get? Yeah.
188.19.
19? Everybody read that? You might think, wait a minute, there's 5 sig figs there, there's only 3 here. When we're adding, it's none of the decimal places we care about, right? Now, the previous page would have meant we were finished, but now we want to do something with that. We're given a certain number of moles of this, and we wanted to turn it into grams. Do not do it this way, okay? So, the calculation that we're making is moles of potassium hydrogen tartrate to 2 grams potassium. I should remove that word. 2 grams potassium hydrogen. Right? Which means moles has to go down here. But we just did that. According to what we just did, 188.19 grams of potassium hydrogen tartrate exists per mole. How many moles do we have? 0.100. Now, if we're paying attention to sig figs, as we always should, we want 3 of them. That's 5, that's 3, but now we're multiplying. So, I don't know. Can you do that one in your head, you guys? Yes? Divided by 10. Now this was all about getting this. Okay. Notice units still cancel. Same stuff we did back in chapter 1 when you were asking yourself, when the hell am I ever going to use this? Here. Any questions? So I want you to reproduce that for all of these. And there may not be enough room, there's no more room here than maybe in the previous page. And you're saying, why do I have to do it 6 times? If you do it 6 times, you're more likely to remember it than if you just write down what I do once. So you only have to do it 5 times because they do one for you. But don't do it this way. Okay? If when I'm looking at the worksheets, if I see it done this way, I'm going to give it back to you and say do it over again. You don't want to do it because this is a hell of a lot of work on this worksheet. So just do it right the first time. Now, that's one conversion, giving moles to get to grams. But what if I'm giving grams and get to moles? Well, I'm so glad you asked, because if you turn the page, that's exactly what you have to do. For all of these, you're given 1,000 grams of each of the compounds and asked to convert the mass to the moles. In other words, what we just did is go here to here. What we're doing on the next page is here to here. Okay? And by the way, we could, if we wanted to, we can also go number of items. Because if I know how many moles I have, remember that conversion factor, 6.02 times 10 to the 23 of anything in a mole? So I could go from here to number of items too. It's gonna be a stupid big number, but I could do that. And there's exercises like that coming up. I just wanna focus on the worksheet. So let's pick one. Look at number 6. What's the mass of that?
Milliliters.
No, the volume is milliliters.
Oh.
What's the mass? What do you know about the density of water, you guys? What is it? 1 gram per milliliter. So if you got 1,000 milliliters, you got a liter of water. What's the mass? 1 kilogram. See how convenient that is? Yeah. If you got 1,000 milliliters, you got 1,000 grams. So there's 1,000 grams of everything, even though that's in volume. And that might mean that the expectation is you remember what the density of water is. And at the very bottom, it says the container with the greatest number of moles in 1,000 grams of a compound is. Well, obviously, you're gonna have to find out what answer leads to the most mass, all right? So, for all of these, you still do this. It's just that this calculation looks different, okay? So, let me do, how about Epsom salts? That's what you throw in your bathtub when you want to have a nice therapeutic soak. What's the chemical name for Epsom salts? In your expertise with formula names.
Magnesium SO4.
Magnesium sulfate
Heptahydrate. Remember I said that it's not septa? Septa is French. Remember what I also said? Somebody in here will use septa on their test? Yeah, more than a few. So, it's septa. Some of the compounds you're asked to deal with in this worksheet, you're given the formula. Some of them you're not. Is it becoming really clear that if you can't write the correct formula, you can't calculate the correct molar mass? If the formula is wrong, everything else will be wrong. That's why I emphasize you have to be able to write chemical formulas properly. So let's do magnesium sulfate heptahydrate. So this is, again, page 1. In 1 mole of magnesium sulfate heptahydrate, we have 1 mole of magnesium, 1 mole of sulfur, 4 and 7, 11 moles of oxygen, and 14 moles of hydrogen. Everyone agree with that? All I do is count the atoms, right? Notice I didn't leave the water together, I pulled it apart. Now I'm going to convert each of these to grams. So moles goes on the bottom. I'm using the periodic table. Molar mass of magnesium, 24.31. The atomic mass is 24.31 atomic mass units. But the molar mass is 24.31 grams per mole. Sulfur, 32.07. Grams of oxygen per mole and 1.01 grams of hydrogen. So in 1 mole of this compound, 24.31 grams grams of it is magnesium. 32.07 grams of it is sulfur. 176 grams of it is oxygen, and 14.14 grams of it is hydrogen. What's the molar mass of magnesium sulfate heptahydrate? No rush. By the way, is everything still okay? Is what I'm doing on the board still making sense?
$246.52.
246.52 grams magnesium sulfate heptahydrate per mole. Now with this type of calculation, I have that. I'm starting here, I'm going here. Okay? So the mass I'm starting with is 1,000 grams. Now it says 1,000 grams. As written, that's just 1 sig fig. So how about we go with 4 sig figs? Let's pretend there's a decimal after the last 0 in 1,000, okay? So the question we're solving is 1,000 grams magnesium sulfate heptahydrate. We want to turn that into moles of magnesium sulfate heptahydrate. Okay? Which means grams goes here. Right? We just figured that out. It's not 246.52 moles per gram. It's 246.52 grams per mole. But because we want grams to cancel, it's on the bottom. Okay? You can kind of guesstimate this. 1,000 divided by 250 is 4. So this is going to be a little more than 4 moles, right? But give it to me to 4 sig figs. One point what? 1,000 divided by 246.52. 0.5.
0.56.
Okay. And what unit? Moles. Nothing to it, right? Really, nothing to it. The arithmetic is just grade 5 math. All we're doing is applying it to atoms and big numbers. Now, just when you thought, this is huge fun, how can it get any more fun? Turn the page. Look at that, ladies and gentlemen. Front and back. So, we did this to this, this to this. For each of these, you kind of have to do everything. So for example, number 2, ammonium phosphate. If you're given the name, you got to write the formula. Okay? Make sure the formula is correct. Sodium hydroxide, the common name is lye, but the chemical name is sodium hydroxide. This, don't do it like that, this is page 1, in 1 mole of, okay? You're calculating molar mass. So that's what this is. So that box is this, okay? And then you're either given mass, converting to grams, or, which is the case here, or moles, converting to mass. Now notice they give 10 kilograms. That's 3 sig figs, but that's not grams. You have to convert it to grams, okay? And do not do it this way. The X's are said, or don't do it this way. Somebody will, but don't, okay? So for all of them, you have to calculate molar mass. And then either this to this, or this to this. I can't conceive of a better test question than that. Because look at all the stuff you need to know to be able to do that. You gotta know how to turn chemical names into formulas. You gotta calculate molar mass. You gotta be able to given mass get moles, or given moles get mass. That's what the standout's all about. And oh, there's a backside to it. Oh my God. Now when is this due? Not next time. But consider this for a second. What if you missed today's class? Okay? This is going to prove foundational to what we do in the rest of this chapter and a real big chunk of chapter 4. Okay? Probably what I'll do next period is I'll give the test back and go through them. This isn't due for that period. It's not even due for the next period. The period after we go through the test, I'll probably give you time to work on this. I want you to make sure you're doing it right, which is why, at least for some of it, I want to be here while you're doing it, in case, if you're not sure you're doing it right. Okay? Pay attention to sig figs, pay attention to canceling, pay attention to units. All the things we did back in chapter 1 when you wondered, why am I ever going to need this? This is why you're going to need it. Okay? And then when we start applying this stuff to chemical reactions and asking, if I have this many grams of this substance and this volume of this solution, what mass of precipitate can I make in the double replacement reaction? This is going to be foundational to all of it. Okay? So we didn't even fill an entire period. We got through the whole worksheet. Oh my God. So it's not everything that's in section 3.2, but it's most of what is in section 3.2. So start working on this. Okay? And again, I strongly suggest that for your benefit as well as mine, you maybe try to do it on separate sheets of paper. I don't care how many pieces of paper you need, as long as I can see that you're doing it, and make sure that what I've done on each page is what you copy precisely in terms of method, okay? And it may seem tedious and repetitive. It's kind of intended to be repetitive. Because if you get tired of doing this because you're doing it so often, then come test time, you're not going to have to wonder, what do I do? You did it ad nauseum already, okay?